circulated the assignment?
No, not yet.
Have you?
No, sir.
Please.
No.
You, as soon as the class gets over, you start, you have to do it. So what is this? The top one? What is the top one? Numerator. Fx of x ds. And the bottom one is the CCD. So this is this probability. So if you look at this one, what is this probability? What is that? It signifies. It is the probability, conditional probability that x will lie between x and x plus dx, given that x is greater than x. It is, and then just a conditional probability. So this one, if you look at it, it is over a small interval dx. So over a small interval, such functions, density functions, do not vary much. So we can define a function at x, conditional density function at x, and multiply it by dx. That we will call it as Rx of x to dx. Because how any density function is being defined, okay, if you have this probability, you introduce a notion of density function. That is, what is density function actually? Fx of x is nothing but probability that in the limit, of course, delta x dx tends to 0. This is how we define the density. You find the probability over a small interval divided by the interval size. This is the probability of x lying in that interval in the limit. The interval size tends to 0. Okay. So in a similar manner, if you have here, this is a conditional density function. We have looked at the conditional density function, okay, earlier. Conditioned on an event, conditioned on the value taken by the random variable. That is, if the random variable takes a value in that range, conditioned on that sum, how do we find the conditional density function? Conditional CDF, everything we have discussed. Okay. Here, this again nothing but the same probability that x lies between x plus dx given this condition. But this condition is little special because it is always that x is greater than x. If you observe a component till that time x and find that x is greater than x, with that condition you recompute the density. So it is just by the conditional density. So we can define this probability can be written as a density times x. So this density we will call it this as the hazard function. Sometimes R is being used, sometimes H is being used because H stands for hazard. Okay, it's a shorthand symbol for hazard and so on. So now we will define. So because we are densities, we are finding only the density Rx of x. So how do we define? How do we interpret it? It is the probability that how do we interpret it? This is how we interpret it. This is the interpretation. So you want to just write the density Rx of x, which is called as the hazard density or so on. It's nothing but here also you should drop the dx. Okay. So if you it's a non-negative value. So if it is, this is the way the density function of a random variable looks like, then what you do is you compute another h or r. How do we find at any given time x? What you do is you find this probability and divide it by this area. Okay, that is, this probability is x and x plus dx. Probability lies between x and x plus dx. Divided by the area till that sweep from 0 to this. That is what this factor is. And divided by the interval size to get the density. So every time you have to recompute such a thing and then draw something. Not sure how it is going to be, something will be like this one. Okay, that function is called as the hazard function. It is the conditional density function, condition that the lifetime exceeds that particular time at which you compute the hazard function. Okay, this is how you can find this. Next, hazard function can be for any given random variable, you can define an hazard function. Let's look at for the case of the exponential random variable. If you have a component whose lifetime is exponentially distributed with parameter lambda, then you know that fx of x is equal to lambda e power minus lambda x. Of course, x has to be greater than or equal to 0. And so on. From that point of view, what will be the density function of this one? Lambda e power minus lambda x, that is fx of x, divided by 1 CCD of this. It is nothing but e power minus lambda. That would give you lambda. Okay. So what the exponential distribution is a one whose the density function takes this form lambda, which is independent of x. Okay, we will call this as the hazard rate. Now, generally, this hazard rate is defined as this. Okay, for the exponential random variable, hazard rate is constant, and that is lambda. For any other random variable, it can be a function of x, because the instantaneous failure rate depends upon the age of the component. More it has age, more it is likely to fail in the next instant. Okay, but because of the memoryless property of the exponential distribution, it never ages. It is as new as it were when we started using it, given that it has been survived, and that is why it is the only continuous valued random variable whose hazard rate is independent of its lifetime. Okay, so that is one important fact. What else? Once you know the hazard rate, hazard function, okay, like this one, it is possible to characterize the entire random variable. That is, we can get the density function, we can get the CDF, everything. So far we have seen that if you know the density function, you can find everything about the random variable. Similarly, CDF. This is also one such function. If you know this, you will be able to compute all moments, everything also. Like MGF is also one such thing, these are. Okay, this is also. How? Because they are related. So Rx of x is fx of x divided by 1 minus fx of x. So what we can write it is, this is d by dx of fx of x divided by 1 minus fx of x. So now, if I compute ln of 1 minus fx of x and then d by dx, then what do I get? This is what I do. But what I am looking for is this. And that will be minus of Rx of x. So that this is, I can write it as minus Rx of x. So I can write this as minus Rx of x. Right? So now if you do an integration, I will write it the other way, minus of integral 0 to t Rx of x dx equal to right? Because I'm introducing t here. Ln of 1 minus fx of t is Rx of t. So you can write it here. Or okay. Plus, actually, there will be there can be a constant here. It will not going to affect me. Okay. There can be a constant here, which I can write it as e power k also. So, if I put x equal to 0, to find that constant, if I put x equal to 0, what is 1 minus fx of 0? That is just 1. X equal to e power of k into e power of minus. This is again 0 to 0, that is 1 only. Okay. So that is e power of k. So e power of k is basically 1. So that the prefactor is 1 only. So this is what we get. So the Hazard function Rx of x is related to the CDF using this connection. So once you are only told about the Hazard function or the okay, then what you can do is you can use this to compute the CDF and then everything else follows from that. The entire random variable can be correct. This is a very important way of writing the CDF. If the Hazard function Rx of t is a constant, say if Rx of t is a constant, which I will call it as c, then what I would have, then fx of x, I will call it as the lambda. Then what happens effectively 1 minus e power of here it is not a function of Rx of x, small x dx. Okay, it is no more a function of x, it is a constant. Then you will have e power of minus lambda. Sorry, this is also I think fx of this has to be t only. That is why it is somehow this t, this is t, and this is also t, and this is also t. Because finally all these things will come in the form of t only. Okay. This is what you get. What it means is, if you have a random variable whose Hazard function is constant, then its CDF will have this form it has to be exponentially distributed randomly. So exponentially distributed random variable has a constant hazard rate, or any random variable having a constant hazard rate has to be an exponentially distributed random. This is what we know. There. Which is the last working day, and there will be a last quiz. Okay, so we will have 13 quizzes. I will take the best 11 out of the 13 quizzes, and that will constitute 60 marks. We will look at some variations of exponential distribution. So what are those things which you look at it? The Erlang, which we have already seen. Then hyper-exponential, then hypo-exponential. And these are all some variations of or some derivatives of exponential randomness. One, the Erlang is the one which you know. It is it's very related to the gamma distribution. Where the parameter is an integer, non-negative integer. Yes, please. Again, I am telling this too early for the next lecture. You can be little late for the next lecture also. You can say. So, what does it mean? We have x1, x2 to xn. They are all IID. X4 random variables with a constant parameter lambda. Then I will call x, which is the sum of xn, has Erlang distribution. Okay. So what is the corresponding formula? Fx of x is lambda e power of minus lambda x over n minus 1 by n minus 1. Okay. Can you recall? This is what I think would have got it. So we have IID random variables, they are all exponential distribution. They have the same parameter lambda, then their sum is as an Erlang distribution, which is given by this one, which we have already discussed. Now what we will do is, we will look at a different case. So what was the use case scenario when you will encounter an Erlang distribution? That is, suppose you have a box, okay, there you have a number of bulbs. And so on. Then what you do is you take one, they are all from the same manufacturer, they are the right at the same, okay, so the same can be characterized the same random variables, and it is inherently exponential random variable with a parameter lambda. So what you do is you take one of them and then put them into use, and then once it has gone you take another, and so on, n such things you do. What is the total lifetime of all the such n bulbs? That is the Erlang distribution. Okay. So this is one use case. The another one is, I have a box wherein I have a number of bulbs or components. They are all from different manufacturers. I put all of them together, and then when I need one, I take randomly one of them and then use it. After it goes away again, one and more, so like that. Okay. But I am looking for the lifetime of a randomly picked bulb. What all I know is that what is the composition of the bulbs from different manufacturers. Okay. So there are n possible types of of the components, and xi is the lifetime of the ith type. Right? Then I also know that what proportion of the component is from ith type. That is, whether it is 15% of the component is from ith type or 23% and so. That I can interpret it as the probability. Okay? So there are n types. Xi is exponential. Xi is the lifetime of the ith type of component. I vary from 1 to n, and it is exponential, and its parameter is lambda. Because they are from different manufacturers, the lifetime can be different based on how well the manufacturing process it, and it is exponential, the parameter lambda. Since I know the proportion of the components in this one, we can write Pi is the probability that an arbitrary component it belongs to type. Okay. So now here arbitrary component is picked that has a lifetime which I will call it as x. It may be from 1 or it may be from 3, I don't even know. Its lifetime is what I want to characterize. So to do that one, we will introduce T, which is an indicator random variable. So all the time we have once I think at least I have mentioned an indicator random variable, but we have not really used it much. Okay, but this will be very useful in order to do a calculation. What we mean by that is this indicator random variable is used primarily to indicate which type that is being picked. Okay, so it can take values 1 to n, and it takes the value I with the probability p. Okay. So T is an integer, non-negative integer value random variable. The value T can take is 1 to n. It takes the value I with the probability Pa. So it indicates, okay, that ith component is the ith component is taken, then T will take the value I, and it will take the value I with the probability Pa. Okay. So basically it indicates which type is being taken. Based on that, the random variable will be assigned a value between 1 to n. That is the significance of the indicator random variable. It takes the value between 1 to n based on what type is being drawn. No. About the x, we will take this point, probability x is greater than t. Okay, not t, you will give the x itself. Probability x is greater than x. X is a lifetime of an arbitrarily chosen component. I don't even know the characteristic, which is what we are trying to find. How do I even tell about it? If I know that type, I will be able to tell. Because every random variable xi, that is being clearly characterized by exponential lambda. That is not known. So if you want to proceed with this one, what you do is you condition the type, in which case you will find out, and then uncondition. Okay. So what you can do is, if you can easily find this one, given t is equal to I, if I ask this one, I will be able to tell. If the indicator random variable takes the value I know it is the ith type, and then this x becomes x. Then this is equal to quantity that xi is greater than x. Moment t takes the value I, x becomes xi. And that is nothing but, you know what this one is. E power of minus lambda I. Because ith component has a parameter lambda. So this conditional probability is easy to analyze. But what we want is this. So now you look at all possible values that t can take, multiply this with the corresponding probability and sum it over the values t can take. So, multiply this probability, conditional probability that x takes a value greater than x, condition that t is equal to I, multiply the probability that t is equal to I, and sum it over all values possible I values, that is from 1 to 8. This is the total probability of this. We have characterized it. So, how do we find out this? This is nothing but this is nothing but this. And what is this one? This is P. This is 1 minus fx of. So x is the one which corresponds to the lifetime of an arbitrarily picked component out of n. X can be, or mathematically speaking, x is a random variable which can be one among the n possible random variables x1, x2 to xn, which are all exponentially distributed with parameter lambda 1 to lambda n. It is equal to xi with a probability p. So x, we will call this as the hyper exponential random variable. Or in short, we use this symbol HED, random variable. So its CDF is can be easily given. So from that other things follow. Okay. So it takes a very simple form. What is its density function is this alone is the density function of the xi. You just multiply it by the probability that x becomes xi and then sum it over. It is the weighted summation of the density function of the individual random variables. Weighted being the probability that x will be that particular random variable x. So from that we can also find the Rx of x, the hazard one, which is simply f, which is nothing but fx of x divided by 1 minus fx of x. This is for HED. We are finding the hazard function for the HED random variable, and that is nothing but PI lambda I. Here there is no lambda. That function of the HED. Next is one more thing. IID random variables, that is, it is x1 plus x2 to xn. Is it written or okay. There are IID random variables. They are all at the same parameter lambda. Now, if they have different parameters and their sum, if you want to find out, how is it? That is, we have got, it's not gamma or the Erlanger, we have to find out. So again, what is the use? How did we, how does Erlang distribution will come into picture? For example, if you walk into an office where you have to face some n clerks to get the service from each one of them, and their service times are all IID random variables with the same parameter lambda, then the total time you spend in each one of the service station is Erlang. But each station or each service may take different time, okay, and it is not identical. The ith one service time is exponential to the parameter lambda. So it is a series of services that you do it. 1, 2, 3 and so on. Then only you will complete and go. So this is exponential with parameter lambda 1, lambda 2 and so on. Then that is exponential hypoexponential. So to derive this, what we will do is, we will take the case of two random variables, okay, x1 and x2, and then we will derive the formula. From that we will generalize. Again, generalization I will not prove it actually, but it will be obvious. So we will just take the case where x equal to x1 by x. There are only two stations. This is one which has the exponential parameter lambda 1, this is the lambda 2. Then we have to find the fx of x. Okay, I will call it as t, fx of t. How do we find it? We will use the convolution. It is the sum of x1 and x2. They are independent, still they are independent. So this the density function of the sum of two random variables is the convolution of the density function. So that will be given by 0 to t fx1 of s into fx2 of t minus s ds. Okay, so we will write it. Okay, this is going to be a little lengthy. This one, fx1 of s is nothing but lambda 1 e power of minus lambda 1 s. Right? It is the density function of the exponential random variable with parameter lambda 1. And fx2 is lambda 2 e power of minus lambda 2 evaluated at t minus s. This is at s, this is at t minus s. Right? So we will take out whatever that is whatever that is possible outside the integral. Lambda 1, lambda 2, e power of minus goes away. E power of minus lambda 1 t also goes away because the variable is s and this is only an limit. So here minus lambda 1 s is there, plus lambda 2 s is also there. So now it's okay. Lambda 1, lambda. So here what will happen is, we put t and if you multiply here, this goes away. This is what we will get. Okay. Again, the way we will write it is, okay, e power of minus lambda 2 t into lambda 2, we will club it with this one, and then we will write lambda 1 by lambda 1 minus lambda 2. This factor I am writing it like this. The other factor is, again I want to put, okay, we'll write it. Why we want to do it? Because we are computing x1 plus x2, lambda 1 with parameter lambda 1. Both are, they are symmetrical. There is nothing, we are not doing x1 plus x2. So this should also be very symmetrical. Whatever that happens for x1 factor, similar thing will happen. Now what really we are happening is that the hypo-exponential PDF is very similar to the, for each one of the x1 and x2, this is nothing but the PDF of x1, but being multiplied by a number. This is just the PDF of x2 multiplied by some number. What is this one? If x1 is what you are going to talk about, you have to multiply it by the parameter of the other random variable divided by other minus. Similarly, if 2 is what you are talking about, lambda 1 by lambda 1 minus lambda 2 is what we have to find. So this will only come here. The other variable will come here. Okay. In the case of here, lambda 1 comes here. The other variable comes in this place. So now this is for 2. It is okay because you can write it like this. If it are 3, what do you do? Then what really happens is, this gives, for each one of them it happens like this. That is, if it were lambda 3, if it were that, both will be lambda 1 e power of minus lambda 1 t will be there. Its own PDF will be there. It will be multiplied by, for everything other than lambda 1, you should write one factor. For lambda 2, it is lambda 2 minus lambda 1. For lambda 3, it is lambda 3 by lambda 3 minus lambda 1. This is how we have to write. With this part I am not going to prove it. Okay? But it will follow. If you really take care, if you do all these, this one is how it goes. If it were one more thing, lambda 4 was that, then it will be lambda 4 by lambda 4 minus lambda 1. So, leave alone this one. For everyone, other things, that parameter will come here, that parameter point at this lambda 1. So, from generalizing this one, we can write some factor like this one. So, the density function of hypo-exponential random variable, it is the sum of the weighted sum of the density function of individual random variables. This is the density function of the individual random variables, and some weightage is to be added, then we will have. What is the weightage? That for ith one there will be one weightage, and n is there because there are n such random variables you are adding. If it were different m, then it will be different. So Cin is I varying from 1 to n. I not equal to, I will put j varying from 1 to n. J not equal to I. Lambda j divided by lambda j. So if it were the ith random variable you are talking about, it will appear only here. All other random variables will have one term contribution, that will be lambda j by lambda j minus lambda. So j varying from 1 to n, j not equal to I. So this is the hypo-exponential random variable. That is again because what you do is, you go through, you take an application, go to an organization, you have to go through n such things, but depending upon your status, you don't need to pass through all n. Maybe you may, after 3 stages, you may have to, you are maybe complete, or 5 stages and so on.